So yeah, so as I said, I want to talk about CUDA Python, and just to kind of set stage, like, what does it mean to have CUDA in a language? Well, CUDA actually is a lot as a whole platform, and it's in exposing the capabilities of a GPU to the different layers that programmers and developers use. So if I just gave you, for example, PTX, which is our virtual machine for very low level running hardware, probably not going to be as useful as giving you domain libraries that target per se just data frames or statistics analysis and so forth. So we think of CUDA in these levels of stacks, and where you're at in that stack often kind of determines where you can move. And usually developers, like if I'm a math library developer, I'm often maybe not going to the hardware layer as much. Or if I'm a PyTorch developer, I'm not going. So if you just take like an idea of like, let's take one uh, kind of very small algorithm, Saxby, which is very common. It's just single precision a times x plus y. Um, if I take this in something like PyTorch, PyTorch gives me a very nice interface. I can just call out the Python, define the function, return with something that looks very much like math, ax plus b. And then its usage, I just call Python objects normally. Here, you don't know that under the hood, this could be run on the CPU or the GPU. You're working in the domain level, and you can be very productive, very fast at working at it. Then perhaps maybe you want to do something that's a little bit more data sciencey, like with data frames. But we also have domain libraries that take things like pandas and gets them to the GPU. And in this case, CUDF would take the same idea where I'm multiplying two vectors of numbers. In this case, they're just parts of your data frame. Maybe I'm pulling in angles and degrees or something like that. But once again, while I'm using a GPU, I don't really know what the effect that the parts of the GPU that I'm using or anything like that. So we moved like one layer down to our array libraries, or is it this array library? Sorry about that. But it takes something like CuPy, and here I'm actually going to say, like, actually I want to create arrays on the GPU, and I want to have arrays on the CPU, and they'll be actually managing those arrays, and I have to know about the GPU in this case. I have to know that parts of my computation is here, some parts of it's on the device, some of it's on the host, and so forth. But I can still do a copy from the GPU to the CPU very easily. It's still very nice in the Python ecosystem. And so just to kind of think through that, a lot of times when we think about exposures of the different abstractions, we're actually looking at like which layer are you at, and there's this kind of notion that like, hey, I'm either going to be highly productive or I'm going to be super fast. I'm going to get like 90% of the hardware speed or something, but I can't be both. And then you can sometimes see these Pareto optimal curves that'll say like you get a pick. You can be a little bit less productive in arrays, but you can be a little bit faster, and so on and so forth. Well, what we're trying to do with CUDA Python is help break that barrier a bit and move you to being both productive and fast. So let's just break down what the ecosystem looks like at these different levels. And so I have a host CPU and I have a GPU, sometimes called the device. And each layer, like code that's going to run on each layer, will will have a host version and then a GPU version or a device version throughout the talk. And today, if you go walk into the CUDA ecosystem, you'll notice like, all right, I have a lot of C++ things from my my host extensions to my libraries that support the language at language features like std_par and exceptions and so forth, to like parallelism libraries like Thrust, and then on the GPU side, CUB, which actually lets the GPU code call their own threads, spawn their own threads, and cooperate together. To math libraries like our linear algebra libraries or neural net libraries, and our device side version of those things, to array interfaces. And then you see in the Python side, those things I just kind of talked through, we have like CuPy, which is the array interface, and Numba, which is a compiler to arrays from Python to LLVM code. And down at the bottom, we have a bindings that will get you on the host, but largely you're calling C++ code to get to the host. And so today, that's kind of if you want to use things in between, there's a big gap, and that's what we're trying to fill. So in that gap, being able to do faster math libraries and your own parallelism and so forth is what we're releasing. So let's start by just looking at how we fill those gaps. The first one is a library called NVMath Python and NVMath Device. So let's get the feel of what I'm talking about here. Take a simple function, ReLU, used in deep learning quite a bit, with a matrix multiply with a bias. Now, if I'm going to run this thing, I'm going to have a matrix multiply kernel. I'm going to have another kernel on the device, the adds, and then I have a third kernel to actually do the linear rectification. So first and foremost, let's just take, if I'm using just C++ bindings, I don't get full Python support. So the first thing we do is add logging and first class support inside Python for like the matrix multiply. But second, you really don't want it to be, you want it to work with Torch and with the other libraries. And so using the specifications of the Python ecosystem, we're going to actually make it so you can interoperate with frameworks. So in this case, like, hey, let's just take some random vectors from that PyTorch example, and add in our own types, our own floats, so bfort16 from Torch, and use those things as our actual arrays and tensors and so forth. The next line here, there's an epilogue. So often in that case, like we said, like if I do a matrix multiply, then I want to add on something afterwards, that plus bias. I don't want to have to launch a new kernel. I want to just say, after you do that matrix multiply, apply this bias function. And so in this case, we provide a bias function, and now you can put it into the same call to NVMath Python, the linear algebra matrix multiply, and here's a Python epilogue. And as we go further, we'll see how to add more and more complex items here. Like this is, all right, you have a little menu that you can pick a few things from, but really we're trying to fuse any Python that comes together. And so like that last line we call fusion, right? If I can launch a single kernel, I will always win because I don't have to pay the bridge, the cost for crossing the bridge from the host to the device. And also we add on a lot of little features such as auto tuning to get the maximum performance. And this auto tuning will work whether you're on the CPU or the GPU. NVMath Python is actually tuned to make it so it works on our Grace hardware as well. So our ARM-based hardware and our GPU hardware. And just to share that these numbers really matter, if I'm looking at the performance of this algorithm and I take a naive approach with my 3 kernels, I'm only going to ever get 76% of performance. But I take this new library that's fusing pieces together, and then we can already get to 90% of my my full performance of the machine. So that's NVMath Python. That's the idea. Like, take the math functions and provide you with the utilities to work on both CPU and GPU, and reduce the number of kernels, but also let you work it with Python as your main language. Okay, definitely check it out. It's on GitHub and releases coming out continuously. Second, let's attack parallelism. Now, just real quick, when we're talking about pushing device functions to the device, in C++, we have this notion of like global, which could be a function that gets called from anywhere, and a kernel, and the kernel being a function that's called on the device. So I can define a kernel here, and I have this funny triple chevron thing that tells me my blocks and my numbers of threads per block, and this will give and call the function with inputs and outputs. So very simple. One fun thing with kernels is like you can't just return from them. So often you're giving an output as a part of your parameters to the function. So in C++, this is the standard. We've been doing this for a long time. In Python, we have the CUDA JIT from Numba, and it provides a similar interface. So I can launch a kernel. I'm using get item instead of like my triple chevron because we're Python and we don't have triple chevron. We don't want to rewrite the language, so we use the parts of the language we had and provide a kernel with a get item and off to the races. So it looks pretty similar, except when you're trying to call something like a function that already exists on the device. So in this case, I take the same idea of a function, but I'm calling the matrix multiply. So instead of having to call in another kernel and having to write my own matrix multiply, I want to call the one that's already provided by CUBE and the team at NVIDIA that's provided very fast BLAS for that device. And so NVMath Python presents a device set of functions, and now I can call it inside my JIT kernel. So I'm on the device. I don't have to call back to the host to call a new kernel. I can call that kernel straight from the device. Now, the way this works is not just like magic where we provide a few items. We're actually coming and trying to bring this whole system to the Python ecosystem so developers can use the entire device and not just parts of it. So we have a ton of CPU, C++ libraries. We have a ton of Python code, but what we really need in the end is like the Python binding calling these things very quickly. So if you think about Python, I've got user-defined functions, my user-defined kernels, and on C++, I have some source code I need to interoperate with. We're using Numba. Numba compiles the Python down to some object codes. We use this C++ compiler. It puts it to object codes as well. And using, now we have to tell the C++ about our code, and we need C++ to tell us about its code. So we use LLVM to generate the appropriate objects, the symbols, and then C++ compilers to bring out the symbols in order to tell the object files how to call each kernel and each piece of the code. And then we use a tool called NVJITlink, which comes in at just-in-time compiling. We'll link all these things together, and we can link all sorts of different types of code, object codes, PTX codes, LTOIR codes. So if you're into like lower level compiler pieces, we're actually really compatible, and that's how we get these bindings. Okay, so you have the full power of these things, and we do all this for you. NVMath device and CUDA Cooperative, which we'll talk about a little bit, like is able to run through these patterns. You mostly don't have to worry about any of these rest of things. So once we have all that technology actually bundled up in a way that can be given to the consumer, let's talk about how we might get parallelism actually on the device. So on the device, we actually break down the device by the whole device, by blocks, which are sets of SMs, and then warps, which are a smaller block, usually I think like 8 pieces. So often blocks will be like around 32. And you can decide how big your blocks are. You can decide how many threads you need, but your warps get scheduled based upon the device. And so sometimes I want to do things very fast, like I want to just have one kernel reducing over just some warp, and then I'll do my own communication. And sometimes I want it over the whole device. So this library called CUB will let you do these reductions based upon whatever level you're at. So in Python now, we're able to actually come in and say, like, let's have just a sum over that particular block. And so so if you look at this code here, it looks pretty messy. There's a lot going on, but the essential piece here is like I have a kernel. It's going to run on my device. I do all my setup of the code. You still got to set up like what threads and blocks and things look like in my temp storage. But now I can actually do things only on the block, whereas that previous kernel we talked about was pretty much ran over the entire device. And so there was no way to break it up and spawn things outside of the particular kernel you had. So now we can actually talk to only parts of my device. And it turns out that when we do all these things, and I know it looked like a lot of like pieces all coming together, and it all gets pushed under the hood inside CUDA Cooperative, we're seeing basically minimal difference between when we're calling block sums and our parallel algorithms in Python versus C++. A lot of that's because we only have to launch one kernel, and we're letting the device actually do all of the coordination of those kernels and those particular threading pieces and cooperation between those threads. And so you can see here we ran it all the way up to many threads, and you can see there's very little overhead, as you will. Okay, so we've added the parallelism ability. So now in Python you can pick which parts of the device you can use parallel algorithms on the device versus host and so forth. Now we'll tackle the language support, because one of the biggest problems we've had is that language support in CUDA, it doesn't always mirror the language support of the surface language. So even in C++, we have libq++ to add exceptions and other nice parts of the C++ language. We have to then bring the exposure into CUDA the same way. So we're introduced a new library called Numba CUDA, which is just taking the the pass in Numba, which is Numba's been the #1 Python compiler for many years, and what we're doing is just taking the CUDA module and now making its own separate module so that Numba can call out to Numba CUDA, and we can independently update it and have backends in Numba CUDA that allows programmers who use Numba to not have to worry about what the particular backend is that they're using. This allows us to bring CUDA features much more quickly, such as the newest and latest floating point specifications and so forth, which I think last year was a big deal. Like, oh, we have a new floating point, we can quantize our models much better, and so forth. Well, you could do that if you were working in C++ at a low level, but in order to get it to work day one in Python, you had to do some magic. And so now we were able to bring those to day one, all the features of CUDA to the Python community through Numba CUDA. Additionally, we're able to now read C++ code and generate the Numba binding. So here's the case where we knew that, like, all right, I have a new piece of code that came out. I need to put, in this case, the brain float 16 into a Torch program. And so this was, when the Nemo team came to us, as we need something to like get these new device these new device floating specification into our kernels. Like, how do we then add that in? Well, in C++, it's a template, so I can just specify my template. But in Python, we don't have templates, so we invented NumbAST, which is a binding tool that actually will read the template of code, dynamically generate the objects as needed, and then can allow your Torch code or any Python code to utilize that templated C++ code. So it's out today, and it's used by Rapid's team and our Nemo teams as well. Now that was the device side. Let's talk about the host side. So the host side, today we have what we call just the Python bindings that are generally just generated from our C++ bindings, and there's basically links out to libcuda and NVRTC, which is the compiler we talked about a little bit earlier. But really what we wanted to do is add the high-level Python object model so that you're not inventing these things yourself, because if you look at Torch or JAX or any CUPy, any of these codes, at high-level codes, they actually invented their own object system for working with our devices. And so we're introducing a Pythonic device object model so you can handle all these, all the various pieces you need to bring together in Python without resorting to extra toolchain items. And so here's a few of those accessors. So just starting from the device, there's a context, you can set it, but really at the end of the day, you're going to have a context when you start dividing things, but you get the option of doing things like having context, but you can manage your streams straight as Python objects, and then for each stream you'll have events and so forth. And then we're currently bringing the memory resources and buffers and so forth like that. So now you can actually work on the parts of the device inside Python and object layer. And as I mentioned, when you're using with Python, you're also JITting a lot of code. So we also provide some of the Pythonic access to the compiler, the runtime compiler objects. And so we might have the program, and like I've been alluding, we've been using C++ on a lot of these things, PTX, which is our low-level interface, but also things like MVVM, which is a LLVM IR layer, specifically for NVIDIA devices. And that can produce any number of types of objects, such as just straight more PTX code or a binary or another IR, which is called link time optimization IR, which will allow you to then change out the various C++ things that you're calling later on. And then you get some object code, and you can actually have your kernels. And all of these things are going to be accessible through through Python, sorry, as Python objects. Now, of course, like if I have a whole bunch of these different object codes coming in from different lower level code, lower level representations, I need a linker. And so now we have a linker object, and it can take in a variety of different object code and produce your kernels. So it's all coming together in this accelerated computing hub where we're showing people how to use these things on GitHub. You can go fork this repo, you can play around with it, make the examples yours, or we can bring us back contributions and so on and so forth. But all this Python work is kind of trying to bring the top speed of CUDA to the Python ecosystem. We encourage you to try it out. Um, I gave you just a slice of what's going on here. I really recommend coming to GTC in March. We have 4 full days of talks, and we have, I think, like 6 or 7 sessions on this Python launch with CUDA. And so I really think that you're going to benefit a lot by if you come and talk to the experts who are all building these systems together. And that's all I had for you, Chris.